Let's introduce a new idea. A vector field F is called conservative if it's secretly just the gradient of some scalar field F. We call F the potential field for F. Picture it this way. F being conservative means somewhere out there there's a hidden landscape and F is just that landscape's steepest uphill direction field. Not every vector field is like this, but many important physical ones are. Gravity, magnetism, smooth fluid flow. Before we go further, a quick piece of notation. There's a shorthand symbol called del, or nabla, written as an upside-down triangle. It's just a bundle of three partial derivative instructions, stacked like a vector. Partial with respect to x, times I hat, plus partial with respect to y, times j hat, plus partial with respect to z, times k hat. It has no value of its own. It's an instruction, waiting to be applied to something. Here's the pattern to recognize. Del applied to a scalar field gives you the gradient, exactly as before, just new notation for something you already know. Now let's meet a brand new operator, curl. Geometric picture. Imagine dropping a tiny paddle wheel into the vector field at some point. If the field around that point is swirling, the paddle wheel spins. Curl measures how much spin there is at each point and around which axis. Curl is calculated using a determinant, a grid with 3 rows. Top row, I hat, j hat, k hat, the direction labels. Middle row, partial with respect to x, partial with respect to y, partial with respect to z, the operation labels. Bottom row, p, q, r, the actual components of your vector field. This gives us the formula. Curl of f equals, open bracket, partial of r with respect to y, minus partial of q with respect to z, close bracket, times I hat, minus, open bracket, partial of r with respect to x, minus partial of p with respect to z, close bracket, times j hat, plus, open bracket, partial of q with respect to x, minus partial of p with respect to y, close bracket, times k hat. Notice the built-in minus sign sitting in front of the j component. That's a common slip point, so watch for it. Let's work through an example. Task: find the curl of f, where p equals x squared y, q equals z, and r equals x squared y cubed z. Step 1. Find the I component. That's partial of r with respect to y, minus partial of q with respect to z. The partial of x squared y cubed z with respect to y is 3x squared y squared z. The partial of z with respect to z is 1, so the I component is 3x squared y squared z minus 1. Step 2. Find the j component, remembering that extra minus sign out front. That's minus, open bracket, partial of r with respect to x, minus partial of p with respect to z, close bracket. The partial of x squared y cubed z with respect to x is 2xy cubed z. The partial of x squared y with respect to z is 0. So inside the bracket we get 2xy cubed z minus 0, and then applying the extra minus sign out front gives us negative 2xy cubed z as the j component. Step 3. Find the k component. That's partial of q with respect to x minus partial of p with respect to y. The partial of z with respect to x is 0. The partial of x squared y with respect to y is x squared. So the k component is 0 minus x squared, which is negative x squared. Step 4. Combine everything into the final vector. Curl of f equals the quantity 3x squared y squared z minus 1 times I hat minus 2xy cubed z times j hat minus x squared times k hat. Now here's a powerful theorem. If f has continuous second partial derivatives, then the curl of the gradient of f is always exactly 0. Geometrically, gradient fields never swirl. They always point straight toward the direction of increase, with no spinning at all. So why does this matter? If you calculate the curl of some field f and get 0, that's a strong hint that f might be conservative. Use curl of a gradient equals 0 as your conservative field detector.